Hello, welcome to this video. So this video will be about a conventional question in paper 1 of DSE about application of trigonometry in three-dimensional space. Okay, so we have ABC, a triangular paper card, and D is a point. Okay, so everything labeled, right? And then we are asked to find BC and BD in set form. So to find BC, so first of all, okay, I'm afraid we need to find CD, in which, okay, you can see CD, that will be the bridge or the common side between the two right angle triangles on the right and on the left. So that's why here, part A, so CD. So here, CD as well as AD will equals to 20 sine 45 degrees, because you can see CD and AD, they are the same, because triangle ACD is right angle isosceles triangle. And then sine 45, so that would be square root 2 over 2, so that will be 10 square root 2 for CD or AD. Good. And then after that, okay, so we can make use of the right angle triangle on the right. So first of all, we found BC, so try to make use of sine then. Sine 30 equals to 10 square root 2 over BC, the hypotenuse. So sine 30 equals to 1/2. So that's why BC will equals to 20 square root 2 cm. And then finally, maybe we can make use of tangent then. So tangent 30 equals to 10 square root 2 over BD. And here we can make use of Pythagoras theorem, okay, to find BD, the third side of the right angle triangle on the right. But here, so we just try to be coherent. So the whole part, so BD will equals to 10 square root 6 cm. So that will be part A. And then in part B1, the triangular paper card in figure 8A is folded along CD. So this is the line, okay, we are going to fold. So that triangle ACD lies on the horizontal plane. ACD horizontal plane. Okay. If the distance between A and B now is 18 cm, so that means this is 18 cm. Okay, so find the angle between the plane BCD and the horizontal plane. So BCD, so that will be the plane now inclined it. So you can see, the line of folding is at the same time the line of intersection. Right, so that's why, okay, along the line of intersection, we try to find a point, okay, in which, okay, this point, okay, we try to have the two normals, okay, of the plane. So you can see for B1, the best point, so that will be point D. And then we try to note that AD is perpendicular to DC, and AD perpendicular to DC, and also BD is also perpendicular to DC, the line of intersection. So the required angle would be angle ADB. So AB is 18 cm. That's crucial because we want to find this angle. Okay, we want to find this angle, and then AD equals to CD. So this is tan square root 2. This is also tan square root 2. And then BD, so that will be the last thing, in last part. BD, so that will be this. So BD is this angle, this side. So BD, so that will be tan square root 6. So that's why here all the three sides be known here. So that's why we try to make use of the cosine formula. So that would be tan square root 2 square plus tan square root 6 square is minus 18 square. Good. And then we make use of the calculator to help us. Tan square root 2 is going to be 200 plus 600 minus 18 square divided by 2 times tan square root 2, and then times tan square root 6, goes out of it. So that will be 46.6 degrees, right? So 46.6 0320866 degree. And that will be for part B1. And then for part B2, describe how the volume of the tetrahedron ABCD varies when angle ADB increases from 40 degrees to 140 degrees. Okay, so I'm afraid AB is not the height, or BD is not the height. The height, so would be this. Okay, so suppose here we try to have the projection of B on the horizontal plane and also on the line segment AD. Okay, so that will be here. So this blue line, will be the height. So that's why here I'm afraid the volume of ABCD, so that will be 1/3 of the base. So that will be 1/2 AB sine C. So that will be just tan square root 2 . Right, so just tan square root 2 times tan square root 2. So it's the base, I'm afraid it should be a right angle triangle, correct? So just tan square root 2 times tan square root 2 and then divided by 2. Right, base times height divided by 2, not 1/2 AB sine C. Anyway, so and then that would be, and then the height, so that would be tan square root 6, and then times a sine angle ADB. Okay. And then if we try to reorganize a little bit, so the denominator is 6, and then 10, so 1,000. Oh, good. So this is 3 then. So 1,000 square root 6 times sine angle ADB. So that's why here, so we have a quantity. So, and then equals to a constant. This is a constant times sine of angle ADB. So that's why this is crucial. This is a must, okay, for us to put that down. So I'm afraid, okay, the volume varies directly as sine angle ADB. So and then here, okay, so inside our mind, okay, so we should have this graph. So the sine graph. So this is 180. So that means, okay, we are talking about this part to this part. Okay, so 40 and 140. Okay, so from 40 to 140. So that's why you can see this part. So first of all, okay, we increase and then decrease. So that's why here, I'm afraid I need to put this here. So I continue to here. So when angle ADB increases from 40 degrees to 90 degrees. Okay, so maybe we can have a bigger sine graph here. Good. So 40 to 40. So this part is 40. And then the next part, okay, will be from 90 to 100. This is not 40. 90. And this is 140. Okay, good. Anyway, so from 40 to 90, so the volume increases. And then when angle ADB increases from 90 degree to 140, the volume decreases. Good. And that's all for B2, as well as the whole question. Thank you for watching.